Hello everyone, today let's take a look at QP 152 where we're looking at the normal distribution. We have a standard normal distribution and we want to calculate basically the first 4 moments of it, and we're going to do that using basically moment generating functions. So the first thing that we should know to solve this question is basically what is the PDF of the normal distribution. So in general, this is the PDF of the normal right here, where we basically have this sigma represents the standard deviation of the normal distribution that we're talking about, and this is the mean. And now we're talking about the standard normal distribution, which just means it's basically a normal distribution with mean 0 and standard deviation 1. So in that case, the PDF will look like this. We're going to replace sigma with 1, so that's going to go away. This is going to go away, and then mu, our mean, is going to be 0. So this is going to go away as well. So we're just going to have this as basically our PDF for the standard normal distribution, so a lot simpler. Now, how does a moment generating function work? Well, it's just defined as basically the expected value of e to the power of tx, where x is our random variable. In this case, it's a standard normal. And when you work this out right here, it basically generates moments for you when you take the derivative and evaluate at 0. So why does that work exactly? Well, it works because basically if you write this in terms of its Taylor series expansion from calculus, basically you just get something like this. You get 1 plus basically tx to the power of 1 divided by 1 factorial plus tx to the power of 2 divided by 2 factorial, etc. It keeps on going like that, right? Next term is going to be tx to the power of 3 divided by 3 factorial, and then etc. all the way up to infinity, right? This is just from calculus. So when I take the derivative with respect to t of e to the power of tx, it's like I'm taking the derivative with respect to t of this whole Taylor series expansion here. So when you do that, this term right here will go away. It doesn't have a t in it, it's a constant. And then this term right here will just end up being x on 1 factorial. That was this term. And then for this term, we're going to just have basically x squared times 2t divided by 2 factorial. These 2's are going to cancel, and etc. Then when you evaluate this derivative here at t equals 0, well then this term doesn't have a t in it, so it's going to stay, but all the future terms will all have a t in them, so they'll all become 0, so they'll go away, right? So now the expected value of this term right here is basically the same thing as just taking the expected value of x. Now when I take the second derivative of that same function, right now this one will go away because it doesn't have a t in it, and then this one right here will just become x squared. Remember, these 2's canceled when we took the first derivative, right? And then we're just going to get all of these extra terms, which will continue to have a t in them. So when we evaluate this at t equals 0, they will all become 0, right? And we'll just be left with x squared. So when I take the expected value of this, I'm just taking the expected value of x squared, and so on. When I take the third derivative and evaluate it at 0, it's going to become the expected value of x cubed. And then when I take the fourth derivative, it's going to become the expected value of x to the power of 4, right? And etc. So that's how a moment generating function works. So now let's just do it in our case where we have the standard normal distribution, and that'll generate moments for us, right? So in our case, the expected value of e to the power of tx, what is that equal to? Well, it's just equal to, basically, since we have a continuous random variable, it's negative infinity to infinity, all the possible values that the normal distribution could take. And then we have this PDF right here, and we're going to multiply that by e to the power of tx. So here it is. I plugged in our PDF for the standard normal. This right here is just the definition of expected value. Now what we can do is I have 2 e terms here, so I can basically just combine them. Let's combine these. When I multiply them, it's like I'm adding up basically whatever's in their powers. So this whole term right here will just basically be e to the power of, well, tx minus 1/2 x squared. Now you'll notice what I can do to simplify this is just basically pull out this negative 1/2. So if I pull out this negative 1/2, then I'm going to have to multiply that by negative 2, right? Negative 2tx, and then I'm going to have this positive x squared. And you can simplify this in here by just completing the square. You'll notice that this is very similar to basically x minus t squared. X minus t squared is just equal to x squared plus t squared minus 2tx. This should have been a t, not a 2, but now you'll notice that these are very similar looking, right? We have this term and we have this term down here. All we have to do is just subtract off this t squared from both sides, right? And then this term right here will just be equal to x minus t all squared, and then minus this t squared. So let me just replace that in there. We're going to have x minus t all squared, and then minus an extra factor of t squared in that power now. So that's going to make it a lot simpler to integrate. Now I can basically redistribute this negative 1/2 to both of these terms right here, and I'm just going to get e to the power of negative 1/2 times x minus t, all of that squared, and then I'm going to be, if I pull out my other e term, then I have plus, well, t squared divided by 2. And now this will be a constant relative to what we are integrating over. We're integrating over x, so we can pull this whole thing out, right? And when we do so, we're going to end up with our whole thing that we pulled out, e to the power of t squared divided by 2 times the integral from negative infinity to infinity of 1 divided by root 2 pi, and then we have this e to the power of negative 1/2 times x minus t squared. And we're integrating that with respect to x, but what you can notice here is that this right here is basically the PDF of another normal distribution. Remember the PDF of the normal, which is something you should memorize, is just going to be 1 over sigma root 2 pi times e to the power of negative 1/2, and then that is going to be multiplied by x minus mu, our mean, divided by the standard deviation sigma, and that's squared. Now you can see that in this basically PDF down here, we have t acting as our mu, right? And then we basically don't have it, or our sigma is just going to be equal to 1, right? Our sigma is 1 and our mu is t. So this PDF down here is for a normal distribution with mean t and basically standard deviation 1. So now essentially what we're doing here is we're just summing up over all the probabilities in a normal t comma 1. And since it's a valid probability distribution, we know that all of these probabilities are going to sum up to 1, right? So this is just going to integrate to 1. You could do it yourself, but this is going to be the easier way, right? This is all equal to 1. So that's it. Basically, the expected value of e to the power of tx, in our case, is just going to be e to the power of t squared divided by 2. That's our moment generating function. So now to start getting our moments, well, we know that the expected value of x, based on the definition of a moment generating function, is just going to basically be the first derivative of this function that we just calculated right here, e to the power of t squared divided by 2, when you evaluate that at t equals 0. Now the derivative of this thing right here is just going to be, well, 2t divided by 2 times e to the power of t squared divided by 2, right? These 2's are going to cancel. It's just going to be t times e to the power of t squared divided by 2. When we evaluate that at t equals 0, we just get 0. That also makes perfect sense because we are dealing with a standard normal distribution, right? X is basically distributed as a normal 0 to 1, and 1, or the 0 right here, literally means that it has mean equal to 0, right? And then to get the expected value of x squared, well, then we just take the second derivative of that same function. So d dt, all that squared, the second derivative, e to the power of t squared divided by 2, and let's evaluate that at t equals 0. So now when I do that, I'm basically taking the derivative of this, right? I'm taking the derivative of our first derivative. It's going to be, if we use the chain rule, e to the power of t squared divided by 2, and then for our other term, we're going to have t times basically just, well, t again, right? T squared times e to the power of t squared divided by 2. When I evaluate that at t equals 0, this whole term right here will be 0 because of this t right here, but this one, we're going to have a 0 in our exponent, so that'll just give me a 1. The expected value of x squared is equal to 1, which also makes sense because we have a standard normal distribution, right? So the standard deviation is 1 here. So the variance is the second moment, right? 1 minus basically the first moment squared. Our first moment 0, so 0 squared, so we're going to get 1 for our variance, and that means our standard deviation is also going to be 1 because standard deviation is square root of the variance, right? So square root of 1 is 1, so we should get that as well. Now let's keep going and do the third derivative, or sorry, the third moment, which we do by taking the third derivative of this right here, so e to the power of t squared divided by 2, and then we evaluate that at t equals 0. So if we take the derivative of this up here, again, we're going to get t times e to the power of t squared divided by 2, and then when we do the chain rule over here, we're going to get 2t times e to the power of t squared divided by 2, and then we have basically, well, we have t cubed times e to the power of t squared divided by 2. We're evaluating that at t equals 0. You can see we have a t in all of these terms right here, so they're all going to be 0, so this is just going to be equal to 0. So we also expect this because, well, it's a standard deviation. The third moment is basically representing the skewness, so we have a standard normal right here, right? It's basically symmetric about the mean, so we expect basically 0 skewness. Also, because it is symmetric, right, our standard normal is symmetric about the mean, basically all of our odd numbered moments are going to be 0. But now let's just do it one more time. Let's take the expected value of x to the power of 4. So d4 over dt to the power of 4 e t squared divided by 2. We're evaluating that at t equals 0. We're just taking the derivative of basically our third derivative, right, to get the fourth. The derivative of this right here by the chain rule, we just did it. The derivative of that, which is equal to e to the power of t squared divided by 2 plus t squared times e to the power of t squared divided by 2. Now the derivative of this one, some more chain rule action. It's getting complicated at this point, but we're going to have basically 2 times e to the power of t squared divided by 2, and then we're going to have our 2t squared times e to the power of t squared divided by 2. And then finally, for the derivative of this one, we're going to have, again, by the chain rule, 3t squared times e to the power of t squared divided by 2, and then we're going to have our final t to the power of 4 times e to the power of t squared divided by 2, and we're evaluating this at t equals 0. So this one's going to go away, this one's going to go away, this one's going to go away, this one's not, this one is, right? So we're just going to be left with, when we plug in t equals 0 here, this is going to be 1, so we're going to have a 2, and then this is going to be 0 up here, so this is going to be 1, so we're just going to have a 1 plus a 2, basically, which is equal to 3. So this is basically the kurtosis, right? And that makes sense as well, because another thing you should know is that standard normal has kurtosis 3, right? It has third moment skewedness 0, it has variance 1, and it has basically mean 0, right? Now, if you wanted to go even further, do it for the general case. Well, we know that basically the expected value of e to the power of tx, right? That's our moment generating function. It was e to the power of t squared divided by 2. So for the general case, we can basically just do a Taylor series expansion of this right here, and let's see what we get. Well, the Taylor series expansion of this will just be when we take the term that we're raising e to the power of, we divide that by 1 factorial. We add that on, right, again, but then we square it, and then we take that over 2 factorial, and then we do that again, right, and etc. all the way up to infinity. So we have a cube divided by 3 factorial and etc. Also, don't forget about that one term in the front that I forgot, right? So basically, if you write this in terms of a sum, we're basically summing, let's say, k equals 0 to infinity, and then we have, well, we have our t squared divided by 2 raised to that power of k divided by k factorial. So that is that Taylor series expansion. We can simplify this right here by basically saying it's the sum from k equals 0 to infinity. If we distribute that k, well, then our 2k will go on the bottom along with our k factorial, and then we'll have our basically t to the power of 2k on the top. Now you can see why all the odd moments are going to be 0, because we're only raising t to basically even powers, right? This is going to be like, essentially, if we expand it out a little bit, it's going to be 1 plus, well, t squared divided by 2 times basically 1 factorial, and then we're going to have our t to the power of 4 divided by 2 squared times 2 factorial, and etc. So since we only have t to the power of even numbers in this expansion, right, if I were to take, for instance, like the third derivative, well, then these two terms would go away here, right? And then this one would still have a t in it. So when we evaluate it at 0, all of these would be 0, every single term in the expansion. But if I do have an even number, for instance, the second derivative, well, then this t squared right here will just become basically, well, 2, and then these will go away, and I'll just get 1, right? So that's why I got a 1 as my basically second derivative. So in general, we can say, well, the expected value of x to the power of n when n is odd, we can break it up into two cases. It equals 0, right, if n is odd, and it's going to be, well, let's figure out what it's going to be when it's even. But then if I have n is even, so n is equal to 2 times some integer, well, then basically I'm going to be taking the 2kth derivative of basically this sum right here. The only term that's going to survive is the one that started off with t to the power of 2k. And up here, when I take the 2kth derivative of that, I'm just going to get 2k factorial on the top. That's what happens when you take a derivative 2k times, right? And then I'm going to have on the bottom, well, just 2k times k factorial because it is a constant. So that's the general case for my moments. My expected value of x to the power of n, it's 0 if n is odd, and it's basically going to be this right here if n is even, so n is basically equal to 2k is what I'm saying. But for instance, just using this formula to calculate the fourth moment, well, we'd have n equals 4, which is just equal to 2 times basically our k value is equal to 2. And in that case, when we plug in k is 2, we basically have 4 factorial on the top divided by 2 to the power of 2 times 2 factorial. And in that case, on the bottom, I'd have 4 times 2, so 8. And on the top, I'd have 24. 24 divided by 8 would just be 3, which is exactly what we got for the fourth moment. So this right here is basically the general form of how you would do it for even higher moments. And it's going to be a lot simpler using this formula than taking a ton of derivatives, obviously. So yeah, essentially this question just boils down to understanding how the moment generating function works, right?